recording soon. Okay, it looks like we're recording here. Okay, perfect. Okay, yeah, well, thanks everyone for coming. We're very excited to present our speaker today. So we're the University of Toronto Antennas and Propagation Student Chapter. And today we have a talk on integrated solar panel antennas by Professor Rayan Baktur from the Utah State University. So just a little bit about Professor Baktur. She's an associate professor at the Department of Electrical and Computer Engineering at Utah State. Her research interests include antennas and microwave engineering with a focus on antenna design for CubeSats, optically transparent antennas, multifunctional integrated antennas, sensors, and microwave circuits. She is affiliated with the Center for Space Engineering at USU, the Space Dynamics Laboratory, the University-affiliated Research Center, and collaborates with NASA Goddard Space Flight Center. Dr. Baktur is an ADCOM member of the IEEE Antennas and Propagation Society and is active in the U.S. National Committee of the International Union of Radio Science, serving as the Vice Chair for Commission B and the inaugural Chair for the Women in Radio Science. She is passionate and committed to electromagnetic education and student recruiting by introducing CubeSat projects in undergraduate classrooms. She is the recipient of the IEEE Antennas and Propagation Society's Donald G. Dudley Jr. Undergraduate Teaching Award in 2013 and has been actively serving ieeeUofT-APS student paper competition and student design contests. Dr. Baktur's lecture will focus on CubeSat development basics, link budget analysis and development, antenna designs for CubeSats and small satellites, transparent antennas, and class projects. But of course, today we're focusing on integrated solar panel antennas. So yeah, feel free to take it away.
Right. Well, thank you so much for such a nice introduction. And also, I am really impressed by the students turnaround and how you have such a nice students run a chapter. So it's quite impressive. Anyhow, I know you are all busy. You are coming here during class time. So let's just get started. So for antennas integrated with solar panel, just at a glance, at this age, we have heard of, we are hearing a lot about renewable energy, green energy, etc. And we are familiar with this kind of solar farms, right? So one thing as engineers we ask is, there are so many surfaces here. What can we do with that? And of course, as most of you here are antennas students or just electrical engineering students. So I think first thing come to our mind is, hey, let's put antennas on it, or let's put sensors on it. Let's just use that space. So just in general, antennas integrated with solar panel can be used for, self-powered antennas, self-powered base stations, self-powered sensors, or wearable self-powered radio. And this one here is a UAV I just grabbed online this morning, in fact. So for example, you could put some either self-powered sensors or just GPS antenna looking up, right? Something like that. So many ways to use it. Things can be made prettier, cheaper, and better. So just back forward a little bit, one thing that I focus on is small satellites. Now, our university has its own small satellite program. So here you see an older satellite, and this one is the one we just launched. So it's actually flying right now, sending back some data. This is a little CubeSat. So this is a student-driven project that we have in our university. So therefore, my application really focus on how do I design antennas for CubeSat that can be better, that can be more safe, that can just do multiple things at the same time. So to do that, first we need to know how the satellite is. This is a small satellite, it's nanosat. This one here is a CubeSat, it's small. So we should look at what we have on a CubeSat. So a CubeSatellite apparently will have power system, that's solar panels, batteries, and management system, telemetry, communication, and the frame. And if you look at this frame, the biggest part, and I need to try to stop this thing. Okay, all right, I should do that. Okay, so the biggest part when you look at the frame, the most thing that you see here are that blue solar panels. So the majority area of a satellite is covered by solar panels. And what it means is, if we want to put an antenna on it, then we will have to either take off some solar cells, or the antenna has to be put on in a different manner. So that's something we will talk about a little bit later. All right, since I talked about our university CubeSat, I thought I will give a quick introduction on the CubeSat. So CubeSats are in nano or pico satellite family. So these are all, so the satellites are classified in terms of their weight. So the bigger satellite weighs more. So the nano and pico satellites are the ones that weighs below 100 kilogram, right? So these guys are miniaturized and standardized, so they can be. So this one here is a 1U CubeSat. So CubeSats are determined in terms of units. So 1U is a 10 by 10 by 10 centimeter cube, and okay, then they weigh somewhere around the 1 kilogram, and then you can stack them into 3U. This one is 3U here, and this one is 3U with deployed panels, so you can make them big. So that's what we have. But again, one thing in general is everywhere of these guys are covered by solar cells because they don't have their own power generating system. Powers are only from solar power. And here are some more examples. This is a half-U CubeSat, and this looks like the one we have for 1U, and this is one of our previous CubeSats, 1.5U, and of course you can make bigger. But again and again, most places of the CubeSats are covered by solar panels. So I know I keep on repeating, but that's the motivation for the work for us. Where do we want to put the antennas? So when the surface of the CubeSats are covered by solar panels. Okay, now you might have seen antennas like these, the popping out ones. So yes, so we could put antennas that will pop out. But note that when these guys are taken up to space, they are all packed into a compartment called P-pod or nano rack. These days it's nano rack. Most of them are putting nano rack. So nothing will be sticking out. You will have to fold the antenna into the CubeSat and put the CubeSat in the nano rack. And then later on, once they got deployed, the antenna will have to manage to open. So if it doesn't open, then we lose our satellite. In fact, this one that we just launched let me see when, December. So basically just 4 months ago, the very first antenna that the students bought did not even pop. So it's not like, you know, what if there's an accident? It really happens. It's quite common too. So therefore, first of all, we don't want to chip off. I mean, if possible, we don't want to chip off some solar cells from the satellite. And second, to put the surface mount antenna so you don't need deployment. Second, even if you don't want to chip out, then we might need deployed antenna, but then that may prompt accidents. So therefore, question here is, can we integrate antennas with solar panels? 1, to save space, 2, to reduce accidents? And the answer is yes. And that's what I will walk you through today on the things that we have done as well as things other groups have done. All right, so first thing come to our mind is, let's put the antennas on top of the solar panel. Let's put it on top so that we don't have to take solar cells out. If you want to put it on top, then the antennas have to be transparent. It has to be really transparent because solar cells, the space certified solar cells, normally have about 30% efficiency. So you can no longer lose more power. So you can't block sunlight. So it has to be more than 90 or 95% transparent. So we do have transparent conductors such as indium tin oxide or silver nanowire, or recently our group has been involved in working with silver nanowire and carbon nanotube hybrid. So those are nice transparent conductors, transparent to our eyes, like we can't really see something, but one, their transparencies, if their transparencies are as high as 90%, the conductor is really bad conductor, that's one thing. Or if you want to have a decent conductivity, the transparency is actually somewhere around 80%. So therefore, we turn our attention to meshed conductors. Like the screen that you have in front of the microwave oven, it lets the light go through, but the microwave does not come out to burn us. So with that idea, we started our first initial studies and prototyping. So here we have a rectangular meshed antenna. So the transparencies is defined as the see-through area over the surface area of this patch antenna. And here are some results. So the way we read it is the first part here is we fix the width of the line. That's what most people did at the beginning. The mesh line, we have the same size of the mesh line. And in that configuration, we found out the higher we make the transparencies, and that means we will have fewer mesh lines, then overall we have decrease in the gain. That makes sense. You have more openings, just there's not enough space to create a cavity or let the surface current go. And the next thing we did is we fixed the transparency. Under the fixed transparency, then we get to make the line. We get to study what does the line width do. So for example, if we have a 70% transparency, okay, and of course we need a 90%, but for now, just for study purpose, let's say we have 70% transparency, then that means if we make the lines very thin, then we can put more lines, right? So that also makes sense that the thinner the line, we have more gain. So this really works for our advantage. So this tells us, it's possible we can have an optimal, transparent, and effective antenna. So great, one thing done. The next thing is, okay, now we are putting the antenna right on top of the solar panel or solar cells. So how do they interact? To do that, here we have a quick model of solar cells and antenna. So oftentimes we will have a in the ground to mount the solar cell. And normally to mount the solar cell, we also have a little thin layer of tape, like Kapton tape that I put here. And then it's solar cell. If it's just a solar cell, then too bad. We cannot really put antenna on top of it because solar cell, it's semiconductive. And it's first of all semiconductive, and second, on the very top of solar cells, there are some like metallic lines to conduct the current. So if you put an antenna, then you just short everything. But again, good news, to protect solar cells from space environment, often they have a cover glass. So that cover glass creates a substrate for us. So with that cover glass, we put the patch antenna on. So this is our fixture. So we made a fixture of a 1U solar panel. So this is a solar panel that fits that 1U CubeSat. And this one is a panel without solar cells. So these two will give us, so testing the antennas on this guy and that guy will, the one with solar cells and one without solar cells will give us some bench line results. So here are some results. So I'm actually presenting the results backward. I'm presenting the results to satisfy the power engineers first. For us, antenna engineers, all we really worry is, hey, how would the solar cells affect our antennas? But the power people is like, don't put anything on top of my cell because that's my only power. So therefore, we need to first tell them, our antennas will not block too much, right? So here are the results. So from top to bottom, it's a bare cell, and then bare cell with cover glass, and then bare cell with cover glass with integrated, just not transparent patch antenna and patch transparent antennas. So from here, we see that the biggest reduction on the solar cell's performance is actually the cover glass. And that's something everyone has to live with. Of course, we have to make the glass more transparent as possible, thinner as possible, not too thin, because if it's too thin, then it's hard for us because we need to use that substrate. So anyhow, from that, so the very bottom one is an antenna that is not transparent. The rest are transparent. So the transparent antenna with this one has like only 70% transparency. We also have results for 90% transparency. A 90% transparent antenna will not affect the solar cell efficiency for more than 3%. And that's a really good news, because when you have a CubeSat, and the CubeSat will carry all types of instruments, right? Those instruments cast shadow on the CubeSat. So the antenna's effect is no more than those shadows. So with that, the system engineers opens the door for us, say, okay, you are allowed to put it on, so we can go from here. All right, next, to satisfy ourselves, how does the solar cell affect our antennas? To do that, we need to know how solar cells are made of. So this one here is a model. So this one here is a model that we extract right here. We extracted using electric microscope. So majority of it is germanium, and then we have these active junction, and then the mesh, the line that conducts the current that I talked about earlier. Now on top, we will put cover glass and then put our antennas. Okay, here are some results. That's at the first look, it's kind of disheartening a little bit, okay? What it says is, right now, let's say we don't know exactly how conductive is the germanium and the doped germanium layer is. So let's say, okay, we're gonna just vary its conductivity to see how it affects the gain. If it's not conductive, fine, it is just a substrate. If it's conductive, like a copper, fine, it's just to raise the ground. So these two will not affect our gain. And we see here, our gain has a big reduction at the conductivity around 1,000 sims per meter. And unfortunately, that's where we were there. That's where we are for conductivity of that photovoltaic layer. So that is the part that when we first found out, like, oh no, are we gonna just work with that? But then the good news is, remember I talked about there's a meshed grid layer on top. Those layers act as an isolation agent between the antenna and the lossy things beneath. So this is a without electrode with electrode. So if we have electrodes, then the gain reduction is not as severe. Another result says the same thing. So one thing is, okay, looks like we are looking at some gain reduction, but it's manageable because of the electrode. And the second thing is, now it also gives us a new research area. We can work with a solar cell designer to optimize those grids, the grids for the current, solar cell current to go, to optimize that grid such that it gives our antenna the best possible gain. So a couple of good news. Here are some test fixtures that we did over the years. We wanted to use these to test all kinds of effect of antennas on solar cell on antennas, 2-cell panel, 1-cell panel, and also work on and also test the antennas on an active solar cell. That means it's connected and we are constantly drawing current. And these are some results here. So we will have to be looking at somewhere between 2 to 3 dB gain reduction due to the lossy solar cell layer, the lossy photovoltaic layer. But again, this is not written on the stone. It depends on the thickness of the cover glass as well as our frequency, but somewhere 2 to 3 dB is what we need to budget. the electrodes, it's possible for us to do the co-design for antennas and the solar cell. Okay, and of course there's adhesive bond. So when we have the solar cell, often the solar cells are bonded with the cover glass with adhesive layer. That very thin layer, it does affect the antenna design, so we need to be careful on that. And what else? So yeah, so these are the element level design. So with that, we can say, okay, so we are confident now. We know we can put like individual antennas on solar panel to make sure the antennas do not block the solar cells, as well as we don't need deployment, right? So that's one thing we are comfortable with. And of course, you might say, hey, the antennas oftentimes should be talking to the ground. That is true. But for Cube satellite, even the bottom of the satellites are placed with solar cells, because when you first launch it, it will be tumbling. During tumbling, you need to make sure you get sunlight from every direction. And therefore, again, transparent antenna is still important for that application. So some extensions. So as you are all extremely creative students, you know, once you study one thing, you always want to ask, what else can I do with it? So earlier we studied meshed antennas, and we learned how to optimize meshed antennas to make it transparent as well as effective. And here is, so these meshed antennas will also give us ways to assemble them to create okay, let's see, this one is, yes, this one is for bandwidth enhancement. So it allows us to do bandwidth enhancement to make so we can put them close by and use the coupling to increase the bandwidth. The more bandwidth, more data rate. Or we can utilize the current distribution and inductive as well as capacitive coupling to create circular polarization. So relatively easier way to create circularly polarized transparent antenna that we can put on solar cells. And this is another circularly polarized meshed antenna. And this one right here, this circular shaped one, this one, it's transparent and it suppresses higher harmonics. So it's kind of like a spatial filter. So if you integrate something like this or this one also suppresses higher harmonic with a transistor to design a power amplifier, then you can suppress the higher harmonics for the amplifier. So the amplifier does not amplify the second harmonic, and then it gives you better power added efficiency or better dynamic range. So several things that we can extend from here, and maybe some of you will continue to extend on that and then come back to teach us what you find. So I do look forward to that. Oops. All right, so we talked about how to integrate antennas on top of solar cells. This one is integration of the antennas under the solar cells. So these two antennas are done by European space agencies. I think the second one has already finished flight mission. So as you can see here, these big squares, those are the antennas. They are placed under the solar panel, and here these slots are placed under the solar cells. So at this time, we don't have to worry about how antennas block solar panels because it's under, right? So that's great. The thing that we need to worry about is how the solar panels affect the antennas. But again, since the antennas are sticking out from solar cells, the effect can be, it will not be too big. That's also what European Space Agency said. The only thing is, over here, as you can see, in order for the antennas to stick out, the solar cells have to be placed with certain spacing. So that, in a way, reduces the efficiency of the solar panel. And this one, the bottom one, since you are putting the slots under the solar cells are custom designed. So if you want to work with off-the-shelf modular solar cells, which is the entire idea of modular type of CubeSat antennas, then these methods can create certain challenge. So therefore, our group moved on to the next one. So we place antennas around the solar cell on the same plane, because oftentimes there is a little gap in between solar cells when you do the assembly. That just for the routing and for the current, DC current. So we could utilize those gaps to create slots, to create radiating slots. A slot antenna is a negative image of a dipole antenna, so therefore it radiates similar to a dipole. So that's the idea here. Okay, that's the idea here. I guess I thought I have some design curve, but anyhow, so I'll just show you the prototype design. This is a circularly polarized, the cross dipole, very easy, circular polarization achievement method just by bending the feed line to create the 90-degree phase shift. And this one is a linearly polarized antenna, but the spacing here, we designed the spacing such that this antenna can be made into dual band. So you can design one set of antenna for uplink and downlink, etc. All right, so let me do a quick summary. So now, so far, we talked about transparent antennas put on top of, integrated on top of solar panel. We also talked about antennas under the solar panel, like the one made by European Space Agency, and antennas placed around the solar cells. So all of these guys, what we have done so far is for 1 gigahertz or up. So for anything below, like for UHF, as you can imagine, the size of the slot or patch, or we don't do patch for UHF, that's gonna create some challenge. Well, of course, some of you might ask, why do we even use UHF? Why can't we just stick to gigahertz? For the satellite, for the Cube satellite, we have uplink. Uplink is from the ground, you talk to the satellite to command it. And downlink is the satellite transmit data for us. So for downlink antenna, no problem. We want to go with S-band or X-band, like higher gigahertz. So we can do downlink directed, more directed antenna direct to the Earth. But for the uplink, the satellite can be tumbling, can be rotating. So in order for us to talk to satellite, to command it at any time, the radiation pattern of the antenna has to be omnidirectional. That means it will have low gain. And then if you look at the phase transmission equations, if we have low gain, then we will have very low power received by the satellite. If the power received is lower, about the same as the noise level, then it means nothing. The satellite will not understand us, right? So therefore, to increase the received power, when you look at here, the biggest factor here is the space loss, right here. The distance between the Earth and the satellite, we can't do anything about, but we can increase the wavelengths. So that means we will lower the frequency. That's actually why the uplink antennas are often UHF, or maybe even, higher VHF. So that's why we got stuck to these deployed wire antennas. So next, how do we replace the deployed wire antenna? So this is one of the solutions. So one of the solutions here is, okay, let's take our slot antenna concept. Let's make the slot around the CubeSat body, such that the way that we have created here. Let's make it along the CubeSat body, and then the system engineer will have to either use different size of solar cells, which they will not like, or use smaller solar cells, and not customized. I'll take it back. These are all modular solar cells. They are sold by places like Boeing, etc. Right? So like that, we're able to get the uplink and the downlink. So of course, if our uplink and downlink are very close, then one set is enough. For this particular project, this one antenna doesn't have enough bandwidth for uplink and downlink, and therefore we made uplink here, downlink here. Since they are both UHF, as you can imagine, we put them very close on a 3U CubeSat. They will couple, they will lock into a new frequency to solve that. we inserted the metallic plane in between the two cubes, which makes total sense because that's very easy to do, and also that helps to isolate some electronics as well. So here is the prototype, and because it's a UHF, in a UHF frequency, we couldn't quite measure it inside our chamber here. So my students took it to the field and set up a field test and did this pattern measurement manually. Like maybe some of you have already done those antenna design challenges in the past as undergraduate students. So you build things on your own, and the measured result matches the simulation quite well. So we were quite happy on that. So we are hoping we could get this flown in the near future. Okay, a minute ago I talked about uplink antenna has to be omnidirectional antenna, and then I said downlink. Okay, then higher gain, more directive is good. We can go higher frequency for more bandwidth. More bandwidth means higher data rate. So that gives us more, space to work with. So for downlink, we want high gain antennas. So far, we've been talking about just individual element design. So high gain antennas, dish, of course, this is something we are familiar with. Dish antenna can give us high gain, or phased array, or this one like NASA's ISARA and Marco. That's like, so that's JPL, so that's a reflector array antenna, etc. So this is the place that we can kind of shine here, right? So, okay, so let's examine how we can do integrated solar panel high gain antenna. So again, this is NASA's antenna, JPL's antenna. In fact, they have flown prototypes of, these guys were flown the one with similar principle over Mars, right? If you just search Marco, you will see it's really fun. So this is a reflector array placed under the solar panel. So this makes sense. So you have solar panel pointing to the sun, reflector array at the bottom to talk to the Earth ground. So question for us. So in this case, the reflector array is just a normal reflector. So question we ask is, hey, what if the sun and the communication end is on the same direction? That's possible, right? For example, if you want to have a low Earth orbit CubeSat talking to TDRS satellite, okay, let me go back. All right. Talking to TDRS satellite, then sun and the communication link is at the same direction. In that case, we can't put this on top of solar panel because it will be blocking the solar panel. So therefore, again, we want to make sure we can design transparent, high gain antennas that we can put on top of the solar panel. So this is integrated solar panel antenna array for CubeSat. So that's a project that we just finished not so long ago. So I will talk about this one a bit more, but questions, how about phased array? Sure, we can definitely consider that. So that means each element has to be transparent, so we can mesh each element. But from the previous, from what we have examined earlier, by meshing the antenna as well as by putting it on the solar panel, we will lose some gain. So that gain will accumulate, and we have the feed line loss, etc. So I'm not saying phased array is not a good option. I just don't think it's as good as reflector array. So we want to continue to examine reflector array. So some reflector array basis here. This is the so what it says here is, for each element, we need to design its shape such that it will give the phase delay that is needed to bend the light to go to the so bend the incoming light to go to the direction that we want. Okay, so design curves. So here are some design curves and what we know from here. So normally this is a general phase curve, looks like something like this. And using that, we can decide on the size of each element. So for a higher substrate, the curve is more steep. Lower substrate, for lower permittivity of a substrate, it can be a little, less steep. So being steep, if it's very steep, then it means each element, the size of each element is going to be kind of close. So that creates design challenge and precision control. I'm not saying it's impossible, but it's going to be more challenging. So therefore, we want to choose the substrates such that it gives enough, range of phase angle that we need. Also, it's not too steep that we cannot fabricate. And here, thin substrate makes it steeper, and the thicker substrate, okay, and having a little bit struggle here. Thicker substrate gives a more, less steep curve, but of course we will lose a little bit of phase angle, but sometimes that's sacrifice we want to make. So what we found here is, all right, so over here so what do we have? Okay, for the same substrate, for the same thin substrate, if we use traditional half wavelength element size, then the curve is really steep. But if we do sub-wavelengths, then we can make the curve, like go down, bend down, and just get it not as steep, not as sharp. So what does it tell us? That means, we can, if we choose sub-wavelength design, then we can use a thinner substrate, thinner cover glass. Earlier, the result in the previous page was telling us, well, you have no choice but to use a thick cover glass. Thicker cover glass, from what we have seen previously for the solar cell testing, it reduces solar cell efficiency. So anyway, so with that, we are able to continue with the design. This is a reflector expand reflector array that we printed with an inkjet printer, and then it was placed on the solar panel, and we feed it with a planar array. We also had to feed it with a 3D printed horn, and the results are as follows. So we achieved about 24 dB gain, and just a standalone of the antenna and on top of the solar panels. Okay, this is a simulation. So okay, so this is the simulation. So this one here, this one here is the printed reflector array on the glass. So that gives us about 23 dB gain. Then on the solar panel, we get 21 dB gain, so about 2 dB gain reduction, which is totally acceptable. So expand, transparent, high gain antenna that we inkjet printed on the cover glass. And we are able to choose a relatively thinner cover glass because we want to go to the sub-wavelength spacing. So sub-wavelength reflector array antenna design. If you don't already know it, maybe look it up. That's really cool. All right, so here I talked about lots of integrated antenna design. Now I'm pulling out something not really integratable on the solar panel, right? Obviously, this is not a conformal antenna. The reason I pulled that out is I thought maybe you'll be interested. So this is a quadrifilar antenna. Quadrifilar helix, called quadrifilar helical antenna, or quadrifilar helix antenna. So that is not a helical antenna. A lot of us at the beginning, we mix them up. So please take a look at their difference. These guys are not helical antenna. Helical antenna is traveling wave, like a wideband antenna. And these guys are resonant type, so they are not wideband, they are not, they are narrow band, and they are not as high gain as the helical antenna. So you ask, then why is it good? Good part is it gives a pattern shape like this. And that's really good on solar, on the CubeSat, because when the satellite just rises from the horizon, that's where when it is not pointed to the Earth, and the pattern like this, we will be using this edges to do our communication. So it gives a good coverage from horizon to horizon. So maybe some of you will be coming up with a solution to have an integrated solar panel antenna with this type of pattern shape that CubeSat people would really like. All right, so there are many emerging designs, and small satellites are getting more and more popular. And you all have heard of Elon Musk's SpaceX Starlink. So I got a picture of those satellites. They are very beautiful. So I like the picture, and I also feel maybe those are the area that some of you will be working on, as well as coming up with solutions where we might have a pattern more like a quadrifilar antenna, but we can integrate it with the solar panel. And it almost is bringing us to the end, but all right. Okay, so I got 2 real stars here. That's great. So I just want to give a quick introduction of Utah State University. So I got this block here, but anyway, this is our university. We are in a very nice valley here. And every year we have a small satellite conference in August. That's where that's the biggest conference in small satellite industry. So all industry, academic, and DoD, all come here to share the newest method, like from launch vehicle to payload and everything. It's really cool. And I work with Space Dynamics Lab, and that is a research foundation of Utah State University. And I figured maybe this doesn't make much sense, because if I just say a Space Dynamics lab for you, because you are, it's just not quite easy to connect with what it is. But I got a picture here. So 2 years ago, there was a comet that we could see. I don't know how many of you have seen that. Maybe you guys can tell me, but I saw that. So 2 years ago, there was a comet. I think it's called the New Wise. I think it's called New Wise. And we could see it with naked eyes. And that comet was called the New Wise because it was discovered by the Wise telescope. And the WISE telescope was made at Space Dynamics Lab. So that's the connection. And I talked about the comet, the stars, and Starlink. What I really want to say is you guys are the real stars. And I look forward to be able to working with you and learning from you. So with that, I'd like to end my talk, and I'd be happy to answer any questions. And again, thank you so much for taking time to do this lecture here.
Yeah.
Thank you.
Fantastic. Yeah, thanks so much for the talk. I really enjoyed it. So yeah, of course, we open up the floor to any questions. You can either turn your mic on or ask them in the chat, whichever you're more comfortable with.
Well, I had a quick question.
Sure, go ahead.
Hi. So earlier you talked about you were talking about UHF antennas in solar panels, and you had a slot antenna, I think, going around solar, like little square solar cells. I was wondering, what was the feed method for that antenna, since it's all in one PCB?
Yes. So you will have to have 2 layers. So the feed method is proximate feed with the microstrip line under the slot. So the ground plane, you cut slot, and then with a microstrip line feed beneath the slot. So
I see.
Yeah, so just a very classic 50 ohm transmission line feed to the slot, and you feed it. If you have, for example, if you have just one single slot, then you will need to feed it closer to the edge, because that's where the impedance is closer to 50 ohm.
Okay. Yeah. And then how did you get that back into the satellite? Did you have like a probe feed on the bottom through the
Yes. Do I not have a breakdown picture? So okay. So yes. So Unfortunately, I think I don't have a picture here, but
That's okay.
yeah, but so from the inside there is a probe. Yes, there is a probe feed from the inside of the cube.
Oh, okay. All right.
Yeah.
That's
So
very interesting.
yeah, so there's nothing fancy there. It's just a very basic microstrip line, and the microstrip line was connected to a probe.
Okay. And then I guess a secondary question, if you were to reduce the frequency further to say 400 to 410 megahertz, would you just increase the height of the slot that you had?
Yeah, so that will be so for the megahertz one, as you can see, in order to get enough length, we meandered it, right?
Yeah.
The lower frequency, it will be more challenging, of course. So we will have to somehow meander it more. On the other hand, for the lowest orbit CubeSat, normally 450 megahertz is great.
Mhm.
So you can go to 300 megahertz, no problem. But if you go lower to let's say like 150 megahertz, then the galactic noise coming to the picture. The galactic
Right.
knock your antenna. So normally people don't go that low. So somewhere around 450 we are kind of safe. But of course, so lower frequency you will have to meander it more. You will have to, whatever you do, you have to have the enough overall length of the slot.
Interesting.
So, yeah, that's kind of like a half wavelength is something we can't quite break. The overall length have to add up to around half wavelength, you know.
Yeah. Okay, lovely.
Yeah.
That was excellent. Thanks so much.
Thank you.
Yeah, thank you very much for the great talk. I'm gonna ask a question. So this transparent reflector that you designed, right? It was an answer to when the solar panel and the reflector are both facing the sun, right?
Yeah. Yes.
I think I didn't quite understand, maybe you explain it, but I didn't quite understand where would be the ground plane of this reflector, because obviously with the clever choice of the unit cells you had a lot of like transparency, right? Because it was kind of like a square ring, but then
so it's just my phone. So this is just my phone. So the solar panel is always built on a metallic structure or a PCB board, right? So solar panel has to be supported by some conductive surface. Yeah. So that conductive surface can be our ground, so normally it's like a conductive surface, solar cells. So what we have is on top of solar cell, we have cover glass and our antenna. So this bottom part is still the ground.
Okay, yeah. So you are reusing the ground of the solar panel, yes. And then, so I would guess like that would change the permittivity, the equivalent, or
that's right,
the equivalent permittivity and the height of your substrate.
That's right. Yes.
Okay, so basically at the beginning when you're designing this transparent reflector, you take into account the thickness of your solar cell and all the materials that you have there.
So when you do the element study, that's a part you do the element study. Yes. So to be more critical, when you do your element study, when you generate that curve phasor, that phase response curve, so that's when you study the complex substrate. And now the thing is for the reflector array, the requirement of the substrate thickness. I mean, relatively speaking, the cover glass will have to be thicker than the element transparent antenna. That's just the individual transparent antenna. So with that much of a thick glass, I should not say thick, but with that much of thickness as opposed to solar cells. Solar cells are very thin. So the thickness of the cover glass in a way is quite a bit thicker than the solar cells. Therefore, the solar cell itself does not quite affect the phase response as much. It will affect the gain, of course, because after all, it's lossy.
Mm-hmm. But so the permittivity of the glass is basically the dominant one.
Dominant one, yes. But to be more precise, as you said, at the element study, you need to study the complex, surface, the thin complex surface.
Nice. Yeah, thank you so much.
Welcome.
Yeah, any other questions from the audience?
Hi, I have a quick question. This is Zach Silva from Georgia Tech. I'm also doing my PhD on transparent antennas. I was just wondering, do you think for meshed antennas that the loss and gain is more due to an impedance mismatch? Basically, you're decreasing your capacitance, increasing your inductance, or do you think it's from a loss in the conductivity?
Yes. So the meshed antenna. So are we talking about only meshed antenna or meshed antenna on top of the solar cells?
Yeah, I was thinking just meshed antenna with the ground plane. Okay. And if you've looked at things with the mesh ground plane as well.
Oh, yeah. So I don't do meshed ground planes. The reason is meshed ground planes, the meshed ground planes will make, too much of a gain loss for me. Okay, so for me, on my side, because our application does not require the ground plane to be meshed, because the solar cell, we don't need the meshed, the ground is solid ground. But if you do the meshed ground plane, then yes, it does affect quite a bit of the gain. Now, as for just meshing, why meshing affects the gain, what you said about, what you said, I think is true. And meanwhile, as you make the mesh thinner, you do have a bit of increase in the individual, you do have increase in the resistance of each line, right? So that reduces the overall efficiency of the antenna. So that can come into the gain reduction, but mainly it's, I think, well, okay, long story short, you take a metal, you mesh it, then the metal is no longer as conductive as the one that is not meshed, right? So that itself just results in the gain reduction. The conductor
exactly.
Yeah.
And has your team noticed kind of the frequency shift compared to, yes, like I don't know how you design them, but do you notice that frequency shift when you mesh it versus solid?
Yes, frequency shift, definitely frequency shift. I have so we have all those results in some previous papers. Right now, I don't remember if the frequency shifted up or down, but definitely frequency shift, impedance change, and of course, changing the gain. But frequency
exactly. Okay.
Yeah, definitely.
Yep. Okay. Awesome. Thank you so much.
Welcome.
Nice.
I have a question. Yeah, great talk again. So firstly, maybe not necessarily totally related to the solar panels, it looks like you guys have a student design team for CubeSats or something?
Yes. So our university is quite well known for a purely student-driven CubeSat team. In fact, I am not even in the team. So I go to their meeting only when they invite us. So it's a really just a undergraduate student-driven satellite project. And they already launched it, and from time to time, they will see me in the hallway and show me new pictures that they sent by the satellite. So yes.
Yeah, that's kind of neat. I didn't know there are teams for that.
Yeah.
The other thing I was curious about, so with transparent antennas, it looks like you have a patch and then you mesh it in order to achieve your transparency.
Yes.
Does it ever, so I know like some fractal antennas, they sort of look already like meander lines and stuff. Is there any benefits of doing something like that rather than trying to mimic a patch?
I am sure there are many ways to do things. So yes, I'm sure there are many ways to do things, but if we want to convince the satellite team or the system engineer to put it on their solar cells, then we need to propose something as simple as possible, right? Any change will make them delay whatever they are doing. So the patch is the simplest. We can just say, hey, look, all we need to do is just a simple patch. We are going to mesh it up. We're going to inkjet print it or screen print it on the glass, and then you can coat the glass with something. So that's the motivation. Just do it do it simple as possible, and as small changes as possible to whatever they have for now.
Okay, yeah, it seems to
Yes.
work well. So
Yeah, but what you said about fractal antenna, you know, like the different shapes, I think they're all excellent solutions as long as you have enough transparencies, or as long as the antenna is small enough. So the antenna does not, excuse me. So when you integrate the antenna on the solar panel, it doesn't even have to be transparent. For example, if you have if it's 10 gigahertz, and if you have a panel of this big, 10 gigahertz antenna is small enough, right? So they might be able, okay, just put it like that. Then if it's 10 gigahertz fractal antenna, then it will be even, you know, smaller and occupied less area. So the transparency is important for like S-band, 2 gigahertz or 5 gigahertz, etc. Or
okay.
important if it's an array. Like our X-band reflector array, it has to be transparent because you cover all the area.
Right. Yeah. Okay. That makes sense.
Yeah.
Yeah. Thanks.
Great. So I think with this we can end the session and the talk. Thank you so much again, Professor Baktur. And yeah, I'm gonna stop recording.
Okay.
Yeah.